Okay, so now we will study the pH curve of strong base with weak acid. So what is a strong base? Like sodium hydroxide, and weak acid like acetic acid. So acetic acid is CH3COOH, ethanoic acid plus sodium hydroxide strong base gives us sodium acetate CH3CONA and water. So let us take our sodium hydroxide in the burette. This is our burette, and this is our conical flask. And our acetic acid is in the conical flask as an analyte. So this is our acetic acid analyte, and of course we have the indicator, phenolphthalein indicator in the analyte, and this is our sodium hydroxide strong base in the burette, sodium hydroxide, and this is called titrant. Anything we take in the burette is called titrant. So this is titrant. So let us draw the pH curve for this. This is our y-axis and this is our x-axis. And we are going to draw this pH curve, and our x-axis is the volume of titrant, which is sodium hydroxide. The volume is in milliliters, and on the y-axis we have the pH scale from 0 to 14, and say this is the midpoint of this, and let me draw a line representing the pH 7. Now since our analyte is a weak acid, acetic acid, so our curve will start from somewhere here and it will go like this, like this, like this, like this, like this, and like this. Okay, so this, the y-intercept is representing the pH of acetic acid because it's a weak acid. Then when sodium hydroxide drops into acetic acid, sodium acetate is formed. So when sodium hydroxide is dropped, we have sodium acetate plus unreacted acetic acid. When all the acetic acid has been reacted with sodium hydroxide, we get a rise in pH, and the midpoint of this rise, that means this one, is the equivalence point. So we say the equivalence point is at pH greater than 7. There is a rise in pH here, and after that all acetic acid has been converted into sodium acetate, and we are still adding sodium hydroxide, and of course there is water everywhere. So we see that sodium acetate and acetic acid will behave as a buffer. So this is our buffer region. and this is our acidic buffer zone. So we have acidic buffer zone here. Now we have the endpoint of this titration, and from the equivalence point we will plot a vertical line crossing at x-axis, and this is the maximum volume of the titrant that is required for and getting the endpoint, and we halve this point, and then we draw a line parallel to the y-axis, and it will cut the curve at some point, and then we trace back it to the y-axis. So point where it cuts the y-axis will give us the pKa of acetic acid. So why it is like that? We know that CH3COOH partially dissociate into acetate ion and H plus ion. We can write the equilibrium constant for this acid as CH3CO negative concentration and H plus ion concentration divided by the concentration of acetic acid. So when half of the acetic acid has been converted into acetate ion, the concentrations are equal, and then we can cancel out this. So we are left with Ka equals to H plus ion concentration. So it means this point, this half the volume, denotes that half of the acetic acid has been converted into acetate ion, and therefore from this plot we can find the pKa of acetic acid. So what are the salient features of this curve? The salient features of this titration pH curves is that the equivalence point is at pH greater than 7. Second, y-intercept is at pH less than 7. We have a acidic buffer zone. Buffer zone is obtained at pH less than 7. We have the flattening of the curve, at pH greater than 7. Yeah, and we can obtain the pKa of acetic acid from this curve. Okay, so now we are going to study the pH curve of strong acid with weak base. So pH curve for strong acid and weak base. Let us take an example. For a strong acid like HCl, it reacts with weak base ammonium hydroxide, and it gives us ammonium chloride and water. So suppose this is my burette. And in my burette I will have HCl, and this is my conical flask. This is my conical flask. I have my HCl in the burette. This is my HCl, and this is called titrant. So anything in the burette is called titrant, and ammonium hydroxide is my analyte. Ammonium hydroxide is my analyte. So let us draw the pH curve for this titration. So this is my x-axis, and on the x-axis we are going to draw the volume of volume of titrant. So here our titrant is HCl, so we are going to use the volume of titrant on the x-axis, and on the y-axis we will draw the pH from 0 to 14, and this is my midpoint at 7, and I will draw a dotted line representing the pH 7, neutral 7. Okay, so since my analyte is ammonium hydroxide, which is a weak base, so my pH will start from here and then go like this, then like this, and then like this, and then like this. Okay, so the midpoint of this here vertical line, this is called the equivalence point. Okay, so the equivalence point is at pH less than 7, and this curve intersect the y-axis, and that pH is the pH of the ammonium hydroxide, and when HCl is dropped into ammonium hydroxide drop by drop, then ammonium chloride is formed, and we still have some ammonium hydroxide left over, which has not been reacted with HCl. And when all the ammonium hydroxide has been reacted, we will see a drop in pH, and then after that we will have ammonium chloride in the solution, and we are still adding the HCl, so like this. So in this curve we will have one buffer zone. This is my buffer zone. So this is basic buffer zone. So the buffer zone is at pH greater than 7, and from the equivalence point we can drop a line parallel to the y-axis over the x-axis, and this will give us the volume of the titrant that is required to completely neutralize ammonium hydroxide. Now if we'll take half this volume and make a line parallel to the y-axis and intersect it to the curve, titration curve, and corresponding to that the pH, this pH will give us the pKa of ammonium hydroxide. So we know that ammonium hydroxide is a weak base, so it will partially dissociate into ammonium ion and hydroxide ion. We can write the equilibrium constant for this base as ammonium ion multiplied by OH negative ion divided by concentration of ammonium hydroxide. Now when half of ammonium hydroxide has been converted into ammonium ion, the concentrations of both will be same, and then in this formula we can cancel them out, and then Kb equals to OH negative concentration. So we see that when half the ammonium hydroxide has been converted into ammonium ion, so that pH is called pKa, and to calculate the pKb, what we will do, pKb of ammonium hydroxide, we will subtract 14, we will subtract pKa from 14. that is 14 minus pH will give us pKb of ammonium hydroxide. So this pKa equals to pH here. So what are the silent features of this curve? The silent features are that the equivalence point is at pH less than 7, y-intercept is at pH greater than 7. We have a basic buffer zone. At pH greater than 7, and the basic buffer is of ammonium chloride and ammonium hydroxide. And we saw the flattening of curve at pH less than 7. So these are some of the silent features. We also saw a drop in pH. After all ammonium hydroxide has been consumed and ammonium chloride has been formed, we saw a drop in pH. Okay, so now we will study the pH curve of weak acid and weak base. pH curve of weak acid and weak base. pH curve of weak acid and weak base. So what is an example of weak acid? So example of weak acid is acetic acid, CH3COOH. And what is example of weak base? Ammonium hydroxide. So they react to give ammonium acetate, CH3COO, and ammonium and water. Let us take ammonium hydroxide in our burette as a titrant, and we will take acetic acid as an analyte in the conical flask. So our ammonium hydroxide here, ammonium hydroxide is my titrant, and I am taking acetic acid as analyte. And of course we have a phenolphthalein indicator here to check the endpoint. Okay, so now we will draw the pH curve for this system. This is my y-axis and this is my x-axis. So on the x-axis I am going to plot my volume of titrant. So which is my titrant? Titrant is ammonium hydroxide. Titrant is ammonium hydroxide. Ammonium hydroxide volume in milliliters. And on the y-axis I am going to plot pH scale, pH, and this is the midpoint of the pH 7, and I draw a line to represent my neutral pH line. Okay, So my analyte is acetic acid, so my pH curve will start from pH less than 7, and it will go like this, like this, like this, and then like this, something like this. Okay, so the midpoint of this, which is called as equivalence point, will be at pH equals to 7. So the equivalence point in the pH curve of weak acid and weak base is at pH 7, and this curve is started from pH less than 7, and this is the pH of the acetic acid. And when ammonium hydroxide drops into acetic acid, it forms ammonium acetate, and the rest acetic acid which remains unreacted. And when all the acetic acid has been reacted with ammonium hydroxide, we have here all ammonium acetate, and then we keep on adding the ammonium hydroxide. So here we have ammonium acetate and ammonium hydroxide. So in this graph we have two buffer zones, one this buffer zone and another is this buffer zone. So we have two buffer zones here. Okay, so from the equivalence point we can drop a line parallel to y-axis intersecting the x-axis here. So this will give us the volume of ammonium hydroxide required to completely neutralize acetic acid, and the half of this volume here we draw a line parallel to y-axis intersecting the titration curve and the corresponding pH. This pH will be the pKa of acetic acid, this point. Similarly, if we go beyond the equivalence point and where our curve ends, so this is our total volume. So this point x and this point y, we take a midpoint of this. So midpoint will start from here and we make a line parallel to the y-axis cutting our original curve, and the corresponding pH at this point will give us the pKa of ammonium hydroxide. So from this pKa we can find the pKb of ammonium hydroxide by subtracting this value from 14. So from here we can find the pKb of ammonium hydroxide by subtracting this pKa by 14. And below here this gives us the pKa of acetic acid. Okay, so what are the silent features of this curve? The silent features of this curve are: equivalence point is at pH 7, equivalence point is at pH 7. Okay, y-intercept started from pH less than 7, y-intercept at pH less than 7, and we have two buffer zones here. One buffer is ammonium acetate, and acetic acid. Another buffer is ammonium acetate and ammonium hydroxide.